I'm recording now.
Okay. Good evening, everyone. Welcome to today's evening lecture. We'll be discussing on the basic concepts and applications of subsurface evaluation. Please, the ground rule for this meeting this evening, to make it convenient for each and every one of us, is that your mic must be muted. And should you have any questions, please just make use of the comment box, or you can signify by raising up your hand, and you'll be noted. When it's time for questions and answers, you'll be called upon. Thank you. So we want to welcome our speaker for today's meeting in the person of Mr. Kenechukwu Ezebialo. He holds a BSc from Anambra State University, an MSc degree studies from Shell Center of Excellence, UNIBEN. And he's an earth scientist currently working with Chevron Nigeria. Please, can we welcome him? Mr. Kenechukwu Ezebialo, you can continue now.
Thank you, Stella, for that warm introduction. You can hear me, right? Please confirm you can hear me.
Yes, can hear you.
Okay. Also, let me try to share my screen. So let me know when you can see.
Okay, it's up now.
It's up. Okay.
Yes.
Just put it on presentation mode. Please let me know when you can see.
Yeah, very clear.
Okay. So without much ado, we are going to basically be discussing the basic concepts and applications of sequence stratigraphy in subsurface evaluation. So, course objectives will be that at the end of this course, participants will be familiar with the concept of sequence stratigraphy and how it evolves. Also be able to define key terminologies in sequence stratigraphy, and then also able to understand the controls of sequence stratigraphy. Be able to identify key processes and interpret the building blocks that will be the genetic units that make up a sequence. And then be able to explain stratigraphic architectural patterns, and generally be able to apply this model of understanding of sequence stratigraphy in solving real life problems. So by way of definition, sequence stratigraphy is the study of rock relationships within a chronostratigraphic framework of repetitive, genetically related species bounded by unconformities and their correlative conformities. I want us to take note of the highlighted words or phrases. These will be very important in the definition or understanding of sequence stratigraphy. So it tells you that it explains how rocks are related, that's relationship of rocks. And it tries to package them according to time, that's chronostratigraphic framework. And then if sequence stratigraphy is repetitive, in other words, you can actually predict from one place to the other. So you repeat, the sequence occurs and repeats again, occurs and repeats again. And it is basically genetically related species. That's species that are similar origin, that are bounded by unconformities. Unconformities will be the surfaces bounding them, or they are correlative conformities. I will explain this further in the presentation. I will show what I mean by correlative, or what correlative conformity means. So basically, sequence stratigraphy is a tool for interpreting time relationships from sedimentary strata. It's also a tool to correlate and map sedimentary facies for stratigraphic prediction. Remember, if you remember what I said in the definition, I mentioned a couple of words, being predictive, repetitive. All these things are jargons and all that we're going to see as we go further in the presentation. And then it's also a model to guide interpretations in data flow areas. If I don't have data in a particular area or the data is poor, I can do, because I expect my sequence stratigraphy to be predictive, to repeat, to be genetically related, I can actually extend my interpretations across those four data areas. Just to mention, for purposes of this presentation, we're just dealing with the basic concept. There are a lot of jargons in sequence stratigraphy. A lot of people say it's difficult and all that, but the basic thing is that whatever school of thought you belong to, just calm down a little and just understand that the things you've learned before now were also difficult. So basically what I'm saying is that sequence stratigraphy isn't rocket science. So we try to look at the basic concept. So going further, if you want to take more courses and all that, advanced courses and all that, to really get a glimpse of generally what sequence stratigraphy means, you can, I encourage you to do that. But for the purpose of what we are doing, is just the basic concept. So back to the presentation, sorry. Sequence stratigraphic analysis integrates many different data sources: seismic, biostrat, outcrop analogs, whatever you can think of. The more data you have, the more you're able to actually integrate, because all the data are subsurface data. All the data are raw, geologic and whatever kind of data. So when you integrate this data, you're able to make more sense or more meaning out of what you're doing. The sequence stratigraphy is not an exception. So in other words, what I'm saying is that the more data you have, the better your interpretation. And then again, it involves the recognition and interpretation of a hierarchy of time significant strata patterns. So what am I saying? You're trying to look at sequences, you're trying to look at parasequences, you're also trying to look at the system chart. These things are subunits, strata units of sequence stratigraphy, and also their bounding surface. So in terms of history, trying to look at how sedimentary geology has developed over time up to the point of sequence stratigraphy. In the 50s, the flow regime concept evolved. So this was generally the free flow and origin of sedimentary structures, where you dealt with upper and lower flow regime to understand what happens with different energy settings. And then in the 60s, plate tectonics evolved, and this basically was incorporated into the analysis of sedimentary processes. And then in the 60s, the finding of porphyria cycles that was discovered by Shell in Holocene of Texas. And then what we are discussing today, sequence stratigraphy, evolved in the 70s, and this basically was used for the stratigraphic architecture of sedimentary beds. So by way of basic concept, all sequence stratigraphic models can be explained in terms of two fundamental concepts, and that would be accommodation space and sediment supply. So the interplay of these two will generally, once you understand the interplay of these two, generally you're already having a glimpse of what sequence stratigraphy is, and the better you will understand it. So the interaction of accommodation space, that's your relative sea level. Here we are discussing geoscience, and sediment supply controls the movement of the positional system, both in the basin one direction, that will be your progression, and the land one direction, that will be your retrogradation. Just for emphasis, progression will be what some people call regression. Retrogradation will be what some people call transgression, right? So generally, accumulation space is that space available for potential sediment accumulation. And this space can be viewed as a combined product of sea level changes driven by eusticity or tectonics, and rate of sediment accumulation. So trying to really understand this, you try to look at the diagram to really have a glimpse of all these jargons will be stated. So I don't know if you can see my pointer, my mouse.
Yes, yes.
So imagine this is the current sea level. In other words, the sea level was below here and then rose over time. So what it means is that this shoreline will change over time. It will either go up or go down. Whichever way, the sedimentation and the point of sedimentation is determined by the position of the shoreline. So as sediments come from land down into the basin, this environment that you have your fluvial actions, your alluvial plain basically, will be where you see your coastal stocks deposited. So as the sea level continues to increase, what it means is that where final stocks were deposited is where that where coastal stocks were deposited initially, sorry, you see final stocks coming on top of it. So the interplay is basically what we're talking about. So in other words, accommodation is therefore a function of relative sea level. And this relative sea level is a function of a number of other things. Tectonic, that's the uplift and subsidence, even your sediment supply flowing into the basin, right? All these things are interplay of what will control your accommodation state. So generally, trying to look at general controls of sequence stratigraphy. Basically, the first one will be your sea level. Over time, I explained before, the sea level will rise and fall. It's rising, it's falling, it's rising, it's falling. So if you now plot the graph of the static cycle over time, you see a sine form kind of movement, right? So if I divide this, for instance, if I call this line a division line, it means that here will be the falling limb, here will be the rising limb. So at each point of this cycle, the position is taking place. So if it is at the highest point, you have your HSC forming. If it's at the lowest point, you have your LSC forming. And if it is climbing, you have your CSC. These basically HSC, LSC, and CSC are basically types of system strata. And HSC means high sand system strata. LSC, we're going to still see all these things further as we go into the presentation. So, but what this slide basically is trying to depict is for us to really appreciate the fact that sea level has a control on sequence stratigraphy. That's your transgression and regression. And then again, sediment supply. So the amount of sediment flowing into the basin also controls sequence stratigraphy. So looking at this illustration here, you see that when you have sedimentation rate in a locality lower than the accommodation space, then it means that the accommodation space is opening or is creating faster than sediment accumulation. You get? So this will tell you a story about the kind of strata stacking patterns you will find. And when the reverse is the case, that's when the sedimentation rate is higher than the accommodation space, the rate of accommodation space creation. You also have a story. And when both of them are equal, you also have a story. So it tells you, hey, going further in the presentation, we'll also still see that. It tells you generally a story about what sediment supply, how sediment supply controls sequence stratigraphy. Again, subsidence is either your sea floor is falling or it's rising. It's either your sea level is rising or it's falling. It's either sediment is coming in or it's coming in so much or not coming in so much. So all these things are factors that affect subsidence, whether that affect subsidence. So in other words, for all we've discussed here, we've also seen that they also affect accommodation space and sediment supply. And in other words, will control sequence stratigraphy. Again, accommodation space. if you look at the illustration here again, you see tectonic subsidence to be C, Eustacy to be E, and then sediment supply to be S, and water depth to be W. If you look at this relationship, you see that the left side is telling you about accommodation creation. That's tectonic plus Eustacy. That's subsidence plus increase in that's rise in sea level, right? It's telling you something about accommodation creation. And then sediment thickness and water depth is telling you something about accommodation use. So the reverse will be the case if we change the sign. That tectonic that was subsidence initially will now uplift. So what will now happen is that it is dropping, instead of creating accommodation space, it is closing it up. The static sea level fall also, instead of creating accommodation space, in the case of the static sea level rise, you see it closing it up. So the same thing applies to sediment loss, which will be the erosion, and then water depth, that's water depth reduction, which is shallowing. So by way of trying to understand the surfaces and building blocks of student stratigraphy, there is a time, I already discussed that there is a time when the sea level is falling, and there is also a time when the sea level is rising. So when base level fall and base level rise here also means same thing as sea level fall and rise, right? So when the base level is falling, you're definitely going to have salt boundaries, surfaces like your sequence boundary, and its correlative conformity. Remember, I'm just going to explain this. Then you have also your basal surface of coarse regression. You have regressive surface of marine erosion. And then when the base level is rising, you have maximum regressive surface. You have transgressive surface, which people also call refinement surfaces. And then you have your maximum flooding surface. For emphasis, this maximum flooding surface is really at the point where the sea level is at this maximum position, landward, right? The point where it gets to, and it no longer goes further back into land, it now wants to go back basinward. So the building blocks will be, remember it's a sequence. These surfaces bound the sequence, and this sequence have strata units, and this strata unit is called low stand system tract, transgressive system tract, high stand system tract, which is your LSC, CSC, and HSC. For emphasis again, a lot of people also define a lot of other types of system tract, your falling stage system tract, a lot of them, right? But for the purpose of this study, or the commonest form of it will be these three strata units. Yeah. So just trying to look at it diagrammatically to really see the key surfaces and the building blocks. So if you look at the red line below and the red line on top, both are sequence boundaries. Sequence boundaries, in other words, they bound the sequence. All right. So if you look at here, I said I was going to explain correlative conformity. If you look at here, you see kind of a sign showing that there was erosion here. So what has happened? Imagine, let's use this place for instance. Let's use the top for instance. Here, the deposition is still very fine. Everything is okay. Imagine the sea level drops to this point. This place is exposed. So instead of deposition happening here, you see erosion, right? And that erosion is what creates that unconformity, right? So, but if you go down deep, because the sea level, this still under the sea, this part is under the sea, you find that that erosion did not take place here. But this place and this place are still the same surface. Both of them are still the same surface. So why here becomes the unconformity. Here becomes the conformable surface that is correlated with this unconformity. That's what is termed correlative conformity, right? So within it, we also have a transgressive surface. That's it. And internally, the building blocks will have an LST. We have from looking at it diagrammatically, LST will form, like I said initially, will form when you have the sea level falling or falling to the lowest point or falling, right? And then you have your transgressive system. You notice that it is relatively thin compared to what you find in your HSC and LSC. This is because the transgressive the transgression doesn't really, most times, is not long lived. So you find the strata pattern, you find the clinoforms not very visible and almost flat lying, and non-seismic almost always very difficult to actually see on seismic. So another thing to note here is that you can also look at stratal termination. You see that your LSC, for your LSC, you have a downlap. In other words, the clinoforms are downlapping on your sequence boundary. And also, it is unlapping towards towards land on your sequence boundary, a downlap and an unlap, right? So again, for your HSC, you have a downlap, sorry, on your transgressive surface. Sorry, on your maximum flooding surface, sorry. You have your downlap on your maximum flooding surface. And in most cases, because this place will be aerially exposed, and then you have erosion here, you have some truncation, just like you find here. Because here you're seeing is a prior HSC. So you can see the truncation I just mentioned. You can see the way this erosion truncated it. So that's basically what you find in terms of key surfaces and building blocks of sequence stratigraphy. So basically trying to look at the architectural pattern. Analysis of complex sedimentary systems involve their description, classification, and eventual interpretation. To this end, sediment depositional settings are characterized and subdivided into hierarchies of genetically related discrete stratigraphic elements, bodies, or units. So just to really show what we've been discussing in 3D, imagine this diagram, see the sea level. So all these places are underwater. All these places are underwater, so the positions are really taking place. You see those clinoforms I mentioned, see the way it is deposited, or it is deposited. So imagine when the sea level falls. If the sea level falls, this place that was underwater is now exposed. And exposing, you now begin to see incision, right? This incision will now be what we were discussing before as unconformity. This basically what is called an incised valley. So at this point, there is no deposition taking place inside this incised valley. What you have happening is erosion, and deposition basically is moving more basinward and going to deposit your low stand farm, right? So this basically is kind of again, imagine that here you have a fine salt here. Because the sea level was there, you have fine salt deposited here. When the sea level drops to this point, just like in this case, you see that all those fine salt that were deposited here is now where you have, remembering that your shoreline determines where your deposition takes place, right? So you now see that where you have fine particles, you now have coarser particles deposited on top of them. All right? And then eventually when the sea level comes up again, you see that place you have your coarse sediments deposited, you have finer particles deposited. So what are we saying? If the sea level is was dropping at the time, I expect to see a coarsening upward, or in sequence stratigraphy, what we call a progradational stacking pattern. If it is retrograding, if the sea level is backstepping, that is coming back landward. So what it means is that final storm is going to deposit on the quarter storm. So I'll be having retrogradation, right? And I'll be having in classical sedimentary geology what they call fining of fault, right? I don't know. I hope this suffices in terms of understanding or explaining it to basic understanding. I'll take this on if it's not clear. So again, trying to look at architectural patterns. We already know the LST, we already know what the TLC is, we already know what the HSC is. So these will be the parasequences that make up the sequence, right? So if, for instance, you look at the parasequences, you see that the parasequences can actually, sorry, excuse me, you see that the parasequences can actually have a different stacking pattern, but generally the sequence will possess another stacking pattern, just like in case of TSC. The parasequences is showing a progradational stacking pattern, but the general sequence, which is the TSC, is generally showing a progradational stacking pattern, finding upward. So HST, we expect it to be crossing upward, that's progradational stacking pattern, and LST, we expect it to be a retrogradational stacking pattern. Remember, I've explained this before. LST is formed when you have some kind of back step or some kind of movement back into the basin, and then HST is formed when you have the sea level almost at the highest point, right? And so just to emphasize it again, if you look at here, you see that incision I talked about, where it's captured. This is basically that unconformity that has been created. This is basically the incised valley that have been created on the sequence boundary due to exposure, due to area exposure. So generally trying to look at industrial applications, sequence stratigraphy is important to study because this approach to stratigraphic correlation helps geologists to solve real-world problems in the exploration for and production of resources. And some of these things will be hydrocarbon exploration and production, mineral exploration, water exploration, and then theoretical study, right? So narrowing it down to hydrocarbon petroleum industry, the hydrocarbon potentials of sequence stratigraphy would be that your high sand system tracks are potential reservoirs because of the high net sand you have in it. Again, you have your low sand also as potential reservoirs, especially your low sand sands. And then your transition system tracks as potential reservoirs, and then in the more distal part, you have them as potential. You have them. That's at the more distal part. Sorry. Then potential fill for low sand reservoirs, right? What I mean here is that I think there's a mix-up. What I mean here is that transitive system tracks are potential reservoirs, but at the more distal part, they are potential fields for low sand reservoirs. Then the maximum flooding surface basically a potential field for transitive reservoirs, and then your sequence boundary a potential field for high sand reservoirs. And that's it. Thank you for your time. Questions, comments?
Wow. Mr. Kaycee, it has been a really wonderful time with you. Thank you so much for the presentation. It was indeed very insightful. Okay, please, I have a question.
Okay.
Yeah, maybe you can turn back to slide 11. I think that's where my question is.
Okay.
Slide 11. Okay. Slide 11. So please, I don't really understand this concept of accommodation. Okay, I think accommodation creation and its use? Like, I don't really get the relationship.
Okay. Remember, we said accommodation space is the space for potential sediment accumulation.
Yeah.
Just like you have a house that is built for potential human habitation, right?
Yes.
So the more houses you have, the more spaces for people to live, right?
Okay. Yes. Yeah.
So as the population is growing, new houses are also built, right?
Yes.
So imagine the population is growing at the same rate at which the houses are being built. Then you see that as soon as the house is built, somebody occupies it. I'm trying to relate it with what we know, the creation and usage. And again,
Yes.
another situation is where the rate at which you're building the houses is higher than the population growth, people that really need to stay in these houses. So what it means is that you're going to find a lot of houses that are not occupied by people. Another
Okay.
scenario is when the population growth is actually increasing faster than the rate at which houses are built. What will happen is that you'll find a lot of people that do not have where to live. I don't know if it makes sense.
Yes, I'm following.
So if that is the case, if you put that in mind, you now begin to look at the fact that something created the accommodation space and something is going to take it up. So when accommodation space is being created, you expect subsidence to come to increase accommodation space. But when it's now uplift, instead of increasing accommodation space, it's going to reduce it. You agree with me?
Yes. Yes.
When you have a sea
Oh.
level
Okay.
rise, eh, you expect it to increase accommodation space. But when you have a fall in sea level, you expect a reduction in accommodation space. I don't know if you're beginning to make a sense of it. I don't know if this helps.
Okay. Okay. So, in essence, you're trying to say that the water depth, the thickness of the sediment is dependent upon the water depth, right?
Not really. Not really. The thickness of the sediment is not dependent on the water depth. The sediment is coming from land. Eh? You remember?
Okay.
So, but where the sediment is going to depends on the volume, on the water depth per
Space.
se, on the space available.
Okay. Okay.
All right?
Okay.
Like I said in the case of population and housing now, if more people are born into the system, eh, the process of giving birth to people, right, has nothing
Yes.
to do with the building of the house. Just that the people that are born will eventually go and live in those houses that are built. I don't know if it helps.
That's true. That's true. Okay. My next question is so what causes this rise and falling of the sea level? Like,
A lot of things, a lot of things. There is a local rise and fall in sea level, and there is also global rise and fall in sea level. But in the form of student stratigraphy, what we are discussing is the global control, global rise and fall of sea level, right? So it could even be, remember it is cyclical, right? So it could be in terms of ice melting, it could be in it could be tectonic, all right?
Okay.
So everything you know that is shaping geology is also shaping sea level.
Okay.
When you
Okay.
talk of tides, when you talk of tides, you'll be looking at the pull or the gravitation from the moon, right? That one is different from what we are discussing. What we are discussing generally is the static sea level changes, and which I think maybe you can look at it. You can look. I think there is a Veil sea level curve, right? Peter Veil actually have developed that, so you can look it up and see what it is.
Okay. All right, then please, my last question. Please just turn to slide 13.
Hello. Hey. Hello.
Yeah.
Hello. This Allen on the line seems I'm very much late.
Please let Ellen welcome Allen.
Yeah.
Tell her please complete your question before Allen comes. Sorry, Allen.
Okay.
I think I was trying to ask.
Okay.
Okay. In slide 13, you made mention of a correlative conformity. Please, can you throw more light on that? I didn't really get the concept very well.
When imagine this, you can see my pointer.
Yes, I can.
It's top sequence boundary. This was formed when the sea level was high up, right? Imagine this sea level drops. You understand? Imagine the sea level comes here. You can see my pointer, right?
Yes, I can.
So if it comes here, what happens is that here is exposed. Here that was originally underwater for the position to happen here have been exposed, right?
Yes.
And so you no longer find the position happening here. Rather, you find erosion. I don't know if you understand.
Okay.
And when that
Yes.
erosion happens, remember, when that erosion is happening, is depositing stuff inside here on top of this sequence boundary, the same layer, the same surface, but deeper inside the sea, right? Such that when the sea level comes up again, another HSC, TSC and HSC is deposited. And then here that you have that erosion is preserved as an erosional surface, which is an unconformity.
Okay.
Right? Having explained that, will now come down to the last sequence boundary for you to see where it has happened already. So this was that area of exposure where you had erosion. You get me?
Yes.
And because it is still the same surface that goes down into the basin, all right?
Yeah.
This place is conformable. Down in the basin is conformable, but up here is an unconformity. So this sequence, but this sequence is bounded by unconformities, which is this, and then eventually when this one forms, and their correlative conformity. This conformity is correlatable to this.
Okay.
I don't know
Now.
if you're clear now.
Yes, I'm very clear. Thank you.
Thank you. So Alan, please.
Yeah, I was saying I came late to have lost everything, like escaped my mind. I was sleeping.
Okay, it's fine. I think it's been recorded. Maybe you will get the recording.
Okay, yes. If I can get the recording, so I'll just go through it tonight. Okay. I so much appreciate. Thank you very much.
Okay, so
Stella.
Yeah, Alan, you are very welcome.
Yeah, I saw your reminder.
Thank you for today's lecture. It was indeed very wonderful. Hoping to have you next time. Thank you.
Okay, thank you so much for
Oh,
your time.
Mr.Kaycee, thank you very much. Oh,
Thank you so much. We appreciate it.
I appreciate